Hi everyone, welcome to another video for research design and analysis. In today's video, we want to provide a soft introduction to statistical power. We're going to focus on the concept of statistical power here. In future videos, we're going to talk about actually calculating statistical power for more advanced design. But our focus today is just to get a grasp of the basic sense of what statistical power is and how it relates to the null hypothesis significance test. So as a reminder, in our previous videos, we talked about the null hypothesis significance test and we talked about the interpretation of the p-value. And we said that the null hypothesis significance test is going to require us to assume that some particular null hypothesis is true. And visually, what that looks like is a null distribution. So here we have a hypothetical distribution centered on 0. To make this 0 point a little more meaningful, let's assume that we're talking about, for instance, the difference between two drug treatments. People take drug A and then drug B, or some people take drug B and then drug A. We're looking at the difference between those two conditions. If the drugs, let's say one of them is the placebo, are equally effective, then the difference between those two should be 0, right? Because if our treatment is as effective as our placebo, then the difference between the treatment and the placebo should be 0. However, if the treatment drug actually has a positive effect or a negative effect, we should observe a mean difference that is non-zero. However, if the null distribution is true, we know we should still observe sample means that are sometimes positive or sometimes negative due to sampling variability alone. So assuming the null hypothesis means we're assuming that the true difference between the means in the population is 0, but it's not going to be unusual for us to sometimes get means that are negative or sometimes get means that are positive. The key question then is, how extreme of a sample mean do we need to observe before we reject this null hypothesis, right? And that relates to the calculation of the p-value. We're going to get some kind of x value that we observed, and then we'll say how likely is it to get an x bar, right, or a sample mean that extreme or more extreme given the null hypothesis. So in the case of a single sample t-test, right, which is probably the easiest case to see descriptively, we might get a sample mean of about 2. And if we're calculating this probability as a one-tailed t-test for this particular distribution, and again, these exact p-values will change depending on what your sample size is, we got a p of 0.023. And if we were doing a two-tailed test, right, where we're going to put 2.5% in one tail and 2.5% in the other tail, we'd say the probability of getting a sample mean that extreme or more extreme, assuming the null hypothesis is true, is about 0.046. So hopefully that feels kind of familiar for now. If that is a little bit confusing, you can go back and watch the other videos on the null hypothesis significance test and the correct interpretation of the p-value, right? But this is in essence what we are doing anytime we calculate a null hypothesis significance test. We're assuming some kind of null distribution, and it's going to be centered almost always on 0. We can center it on other values if we're interested in those. But in general, right, then the distributions might get a little more complicated depending on the type of statistic we're interested in. But we want to know what kind of sample statistic should we observe, assuming nothing was actually going on. And then if we observe something unusual, right, provided it's sufficiently unusual, and we usually set that cutoff at a p-value of 0.05, then we'll say it's statistically significant and we're going to reject the null hypothesis and say, hey, I think there might be something systematic going on. It's unlikely this result is due to sampling variability alone under the null hypothesis. So statistical power is the probability of detecting an effect given that the effect is really there, right? But kind of really there or a real effect is usually some kind of approximation that's being informed by past work. And we'll talk a little bit more about these assumptions as we move forward, but that is something that I really want to emphasize here, is that the power analysis that you do and the answer you get back really depends on the assumptions that you make, and therefore your power analysis is only as good as the underlying assumptions, right? Like anything else, we're relying on certain assumptions. With the null distribution, we can have a really strong reliance on that because we know from the central limit theorem that regardless of the parent population, the sample distribution of means is going to be approximately normal. So we can make a really strong assumption there kind of broadly across scenarios. But for some of the other things that we need to assume, we have to be very careful and very selective in how we make those assumptions. And we want to make sure that they're grounded in reality and really grounded in evidence. Practically speaking, we can see an example of that, right, if we contrast two distributions. So again, in red, we'll have our null distribution where we assume that the null hypothesis is true. And in blue now, we're going to have our hypothetical distribution for the real effect, where we assume instead that the true mean in the population is 0.5. And we can now contrast these two sampling distributions to see how much they overlap. Again, the red distribution assumes that the null hypothesis is true, and the blue distribution is a specific case of assuming the null hypothesis is false. We could have assumed that the true sample mean was, 1 rather than 0.5, or maybe even 2 rather than 0.5. But hopefully we have some good reason, likely informed by past work or informed by what the minimal clinically important difference, right, in our scale is. But we're going to assume that the real effect of our drug treatment, right, is 0.5. The treatment is going to confer a 0.5 benefit above and beyond the placebo. So now we can draw our alpha rate, right, where we set the type 1 error rate for our null hypothesis significance tests. In this case, just to make this a little bit easier to visualize, let's say that we're going to do a one-sided test. So we're specifically interested in if things are equal to or greater than the upper 5% of the distribution under the null hypothesis. If they cross this line, we would say it is statistically significant. If they do not cross this line, we would say that is not statistically significant and is therefore a more equivocal result. So by drawing that line, right, we know under the null distribution, 5% of the distribution will be past that line. Where statistical power comes in is how the other distribution, though, relates to that line. So let's look at the left-hand side of these two distributions then, relative to our cutoff for statistical significance. Again, under the null distribution, right, those would be true negatives, because if the null were true, anything that falls to the left hand of that line, we're not going to declare statistically significant, and that's the correct decision if the null is true. So those are true negatives. However, if the null is false and our blue distribution is correct, then anything to the left of that line is going to be a false negative. And in this case, that's bad news, because assuming that the true mean is 0.5, we have a really big chance of making a type 2 error here, right? And again, type 1 errors are our false positives, type 2 errors are our false negatives. And in this particular case, if you actually calculate the area under the curve to the left of our significance threshold, the beta is 0.927. So about 93% of the time, we would be saying that the result wasn't statistically significant, even though the real effect was 0.5. So that means we are pretty underpowered in this study, because if we take the reverse probability and do 1 minus the beta, that means we only have a 7% chance of getting a true positive if these are the two distributions that we have. So this is pretty bad from a statistical power standpoint, because it means we're kind of setting ourselves up to potentially make a bad decision. If we really think that the effect is 0.5, we need to design our study in a different way to give ourselves more statistical power. And in the next couple slides, I want to talk to you in detail about how we can actually do that and improve statistical power in our studies. But first, kind of just as an analogy, how should we think about statistical power? And this is a Gary Larson Far Side cartoon that I really like. Statistical power operates a lot like magnification, right? And the magnification that you need to study a mammoth is different than the magnification that you need to study a flatworm, which is different from an animal cell, which is different from a virus. And if you know something about the organism you're trying to study, you can bring the appropriate magnification to the table the first time around. Now, naturally, right, like you might subsequently develop more nuanced hypotheses and need greater magnification to understand some things. But in general, right, the tools that I can use to study a mammoth are fundamentally different from what I need to study a virus. And the same is true when designing studies in other sorts of experimental sciences. If we know something about the object we're trying to study, we can choose the appropriate amount of magnification, right? Or that is to say, we can choose the appropriate amount of statistical power to make sure that we're asking our research question in a robust way. So what are the factors that affect statistical power? Not surprisingly, they're all the factors that we've talked about, in our previous videos so far, right? We have effect sizes and sample sizes that are going to tilt this toward more certain, and variance in the data that is going to tilt this toward less certain. And then there will be a fulcrum, which are the values that we set for our inferential statistics that determine just how certain we need to be before we make a statistical decision. So one of the major things that we can do in terms of increasing statistical power is if we increase the size of our effect. So going back to, our drug study example, let's say that rather than assuming that I will have a 0.5 difference between my treatment and placebo, I'm going to give a much higher dose of the treatment, and now I expect a 1.5 mean difference at that dose. So by making a larger effect size, by giving a greater dose of the drug, really kind of giving the biggest sledgehammer application of my manipulation that I can improve my statistical power. The width of these two distributions is the same, right? And our null distribution is not going to change throughout any of this, right? But again, we draw this alpha threshold right in the same place, putting 5% in the tail of the null distribution. But now 76% of the alternative distribution is to the right of the statistical significance cutoff. And that's good news, because that means then that I've probably designed my experiment correctly, right, to have, if the effect is indeed that large, I have a very good chance of finding a statistically significant result if that result is there. Similarly, the variance in our data affects power, and because this is based on the sample distribution of means, we have two different methods for altering this variance. Remember that for the sampling distribution, it's really the standard error, not just the standard deviation that we're interested in, and two things contribute to the standard error. One is the standard deviation or the variability of the data. The other is the sample size, right, the square root of n here. And if I change either of those things, right, I can actually improve my statistical power, either by increasing my sample size or by decreasing the variability in my data. Both of those things are going to have the effect of increasing statistical power because the standard error is going to get narrower. We can see that a little more clearly, right? So again, keeping our mean centered at 1.25 here for the alternative distribution, you can see now that both our null distribution and our alternative distribution have gotten a lot tighter because that standard error has gone down. But again, I'm always drawing the type 1 error cutoff to put 5% of the data in the tail of the null distribution. And now I have a 99% chance of rejecting the null hypothesis in this situation, right? So if I've given my drug in a much higher dose and I've recruited now a much larger sample, I have a very, very good chance of finding that effect, assuming that effect is real. And that's good news, because that means then, A, if I am confident that my effect is there, I have a good chance of finding it in my experiment. But also it means that if I don't find that effect, that suggests one of our assumptions underlying this power calculation was incorrect, right? And probably most likely, we might have had a poor choice of the effect size, and maybe the true effect is actually weaker than we thought. Right? Because if I enter into a study and I say, hey, I've got a 99% chance of hitting this target, and then I don't, that should maybe give me a little bit of pause and reevaluate some of the assumptions that went into that power calculation. So one of the benefits of having a high degree of statistical power is that it can actually be useful in evaluating some of your other assumptions outside of the null distribution and say, hey, maybe we don't have a good handle on the effect size, or maybe we don't have a good handle on the variability, and maybe we really need to kind of rethink how we're operationalizing this research question, because clearly we don't actually have a good understanding on it as we think we do. Now, the final thing that's going to affect power here, right, is shifting that fulcrum on our lever. And if we change the type 1 error probability, we can affect statistical power. So if you go back, to the video on the null hypothesis significance test, we talk about how the rate of false negatives and the rate of false positives are inherently interrelated, and we showed some kind of 2x2 decision tables to make that case. Here we can show that a little more clearly if we actually draw these two sampling distributions. So going back to our example with a wider standard error, right, but again, our null distribution is centered on 0, our alternative distribution is centered on 1.25, and now rather than putting 5% of the null distribution in the tail, I'm going to put 10%. So rather than an alpha of 0.05, right, I'm choosing an alpha of 0.1, and I'm shifting my threshold for declaring a statistically significant effect back. So essentially, I'm more liberal. I'm going to declare more things statistically significant, and I'm separating the upper 10% of the distribution from the bottom 90% of the distribution. So, right, that makes us more likely to commit a type 1 error and have a false positive. However, as you can see, it also improves our statistical power. So, I go from 76% to 86% in this specific example. So I can move alpha to improve my statistical power as well. And yet first that might give you a little bit of pause because you're worried about type 1 errors, and that's a fine intuition to have. But the question becomes, what's more important, a type 1 error or a type 2 error? Right? And those probabilities are inexorably intertwined. We can't get away from one, right, and have perfect confidence. So if we move the probability of making a type 1 error, we might be comfortable saying, hey, false positives are a little less costly right now, for instance, maybe in a more exploratory phase of research. And we really want to kind of open the door and make sure we're not missing anything, right? We want to avoid any false negatives, because if we kind of get a result here and the next thing that we're going to do is another study anyway, then it might be that a false positive isn't so bad, and ultimately a false negative is the more consequential error. So I might consider moving my alpha level a little bit in order to improve my statistical power. So again, these factors all go into statistical power, and in subsequent videos we'll talk about how to actually do these power calculations in different scenarios. But in a classic a priori power analysis, we make certain assumptions about these different factors, usually in order to solve for the sample size. So there are different ways of going about this. For instance, you can do things like a sensitivity analysis that we'll talk about later. But for a priori power analysis, usually what we're just doing is setting up at the start of the study to make some assumption about effect size. And this might be, some number from the previous literature when people have shown if we do this kind of study, we expect to get differences of roughly this size. Or like, especially in clinical literature, a lot of the time, this is going to be the minimum clinically important difference in that has been established by past literature. So if we say it's a 5-point change on this scale is what is actually meaningful for patients, then we want to make sure that we can detect a 5-point change. The other assumption that we're going to have to make is something about the variance, that standard deviation, right? How variable do we think scores are in the data? And that is actually where we will often use pilot data in order to get some kind of assumption of that variance if there's not sufficient previous research in the field. The next thing, though, that we have to choose, not necessarily make an assumption about, right, but choose is the balance of type 1 errors and type 2 errors. And by convention, a lot of the time alpha is set at 0.05 and beta is set at 0.2, which means that statistical power, which is 1 minus beta, is set at 0.8. Right? And again, like, these things are mutable. You can make a case that the cost of false positives is greater than the cost of false negatives. And as long as you have a logical and evidence-based argument to back that up, I think that's a very reasonable thing to do. But by default, we often say basically false positives are about 4 times worse than false negatives because we set that error rate to be about 4 times lower. So, is that a great starting point for assumptions? I think it's reasonable in a lot of cases. But again, you will have to make a choice and defend it for a particular experiment and for a particular context that you're working in. In general, though, I would say this is a very helpful benchmark for people to use. And if you're working on the more exploratory end of the spectrum where, basically the next thing is going to be another experiment to replicate anyway, maybe you can move your alpha level up a little bit to 0.1. Right? And that would be an appropriate choice there. In contrast, if you're on the more confirmatory end of the spectrum, right, and a lot of research has been done in this area, and we say, hey, we really can call our shot because we know what this should be, we know what this should be, right? We want to set a very high level of evidence for ourselves, right, to basically show that we have a very good understanding of this effect. Then you might ultimately set alpha to a higher level, and you might actually demand a higher bar for statistical power as well. But once all of those things are in place, then what this allows you to do is actually solve for the number of people you need in order to reliably find that effect. So again, if we set beta to 0.2, that means our statistical power is 0.8, and maybe our sample size tells us we need 100 people to have a statistical power of 0.8. And what that means is, assuming all of our other assumptions are correct, we should find our effects statistically significant 80% of the time. But again, right, that depends on all these assumptions being correct. And one of the tricky things, right, is that you're going to have to do this for each statistical test or each dependent variable in your study if they're all different. Or you might do this for a single dependent variable and say, well, this is our primary outcome. This is what my study is really focused on finding. Everything else I might be underpowered to do. We'll look at it, we'll explore it, but this is the thing that I'm powered for. So that's what I'm really focused on. And that's what you should essentially put more weight on, because I'm calling my shot in that situation. Whereas with exploratory research, I'm not necessarily calling my shot in advance. That doesn't mean that it's bad, right? It just means that we have to then probably replicate it in subsequent studies in order to make sure that we have a really good understanding of the eliciting conditions and the construct that we're trying to study.